There's something unsettling and exhilarating about staring up at the night sky and realizing we still don't know what holds the universe together. We can map galaxies, rewind the cosmic clock to the Big Bang, even detect ripples in space-time itself. But what if all of that is just the surface of something far stranger? What if the real architects of reality are invisible forces, hidden fields weaving the fabric of existence in ways we're only beginning to imagine? Picture this every second. Trillions of unseen ripples pass through your body, carrying messages from the birth of the cosmos, shaping matter, energy, even time itself. These aren't science fiction, they're hidden fields, the universe's best-kept secrets, and they might rewrite everything we thought we knew about reality. Think of space as an ocean. We've been studying the waves, planets, stars, black holes, but beneath them lies something deeper. Hidden fields could be the currents, the invisible forces pulling strings behind the scenes. Some might guide particles like cosmic puppet masters. Others could explain why the universe is expanding faster than it should, or why gravity feels so weak compared to other forces. And then there's the wildest possibility. What if these fields aren't just physics, but threads connecting us to other dimensions or even other universes? The implications are dizzying. If we crack their code, we're not just solving cosmic puzzles, we're tapping into the operating system of existence. That's what makes this journey so thrilling. Hidden fields aren't just abstract math, they're clues to the universe's greatest mysteries. Dark energy, consciousness, even the arrow of time might trace back to these shadowy layers of reality. And here's the kicker. We might already be brushing against them in labs, glimpsing their fingerprints in quantum experiments or anomalies in deep space observations. So today, we're pulling back the curtain. We'll explore 30 mind-bending theories from the eerily plausible to the edge of speculation that could change how you see, well, everything. Buckle up, the universe is about to get a lot weirder. Take the deepest void of space, the blackest, emptiest patch between galaxies, and here's the cosmic twist: it's not empty at all. What looks like nothing is actually a seething, bubbling ocean of quantum activity. Even in a perfect vacuum, particles flicker in and out of existence like cosmic static, vanishing almost as fast as they appear. These are quantum vacuum fluctuations, and they're proof that nothing might be the most misleading word in physics. Imagine spacetime as a calm pond, except every drop of water secretly contains trillions of microscopic fireworks, each one a particle-antiparticle pair born from raw energy before annihilating in a flash. This isn't theoretical. We've seen it in labs where these fleeting disturbances subtly tweak the behavior of atoms and light. But the real mystery, what if these flickers aren't just background noise? Some physicists suspect they're glimpses of a hidden energy field, a cosmic undercurrent shaping reality itself. One clue lies in the Casimir effect. Place two metal plates incredibly close together in a vacuum, and they're inexplicably pulled toward each other. Why? Because the space between them is too narrow for certain quantum fluctuations to fit, while outside the plates the frenzy continues unabated. The result? An invisible pressure, almost as if the vacuum itself is pushing them together. This eerie force suggests that empty space isn't passive. It's dynamic, humming with energy we can't yet fully measure. And if the vacuum holds this much latent power, could it be the source of dark energy, the mysterious force accelerating the universe's expansion? The implications get wilder. Quantum fluctuations might also hold the key to gravity's puzzling weakness. While other forces like electromagnetism are strong and immediate, gravity feels faint, almost diluted. One radical idea: gravity could be leaking into extra dimensions through these fluctuations, its strength sapped as it spreads across realities we can't perceive. It's like trying to hear a whisper in a hurricane, the signal's there, but drowned out by the chaos of the quantum foam. If true, hidden fields might not just influence our universe, they could bridge it to others. Yet the most tantalizing possibility is that we're standing at the edge of a paradigm shift. What if these fleeting particles aren't anomalies but echoes of a deeper structure, a hidden lattice of energy dictating how spacetime bends, how particles gain mass, even how time flows? The math hints at it, the experiments tease it, and if we're right, the universe isn't just stranger than we imagined, it's stranger than we can imagine. Every so-called vacuum might be a silent conductor, orchestrating reality from the shadows. The Higgs field is like the universe's silent sculptor, an invisible force responsible for something we take for granted, mass. Without it, particles would zip through space at the speed of light, never clumping together to form atoms, planets, or even us. Picture a room full of physicists at a crowded party. Some move through effortlessly, while others get stopped every few steps by eager colleagues wanting to chat. That's the Higgs field in action, particles gaining mass by interacting with it, like those physicists slowed down by conversation. The more a particle feels this field, the heavier it becomes. Electrons barely notice it, quarks, they're practically weighed down by it. But what if the Higgs isn't alone? Some theories suggest an entire family of undiscovered scalar fields, cosmic siblings with equally strange powers, could be lurking in the shadows. These wouldn't just give particles mass, they might shape the very fabric of reality in ways we're only beginning to grasp. Take dark matter, for example. That mysterious substance outweighs visible matter 5 to 1, yet it refuses to interact with light or ordinary particles. Could an unknown scalar field be the mediator, connecting dark matter to our world through some hidden handshake? Or consider dark energy, the force stretching the universe apart. If the Higgs field is a cosmic brake pedal, could another scalar field be the accelerator, pressing down on empty space itself? The possibilities get even wilder when you consider how these fields might interact. Imagine two tuning forks vibrating at the same frequency. Energy can leap between them effortlessly. Now replace those tuning forks with scalar fields. If conditions were just right in the early universe, energy might have cascaded from one field to another, triggering cosmic phase transitions that reshaped the laws of physics. Some theories even suggest these fields could leave behind cosmic scars, defects in spacetime like domain walls or cosmic strings threading through the universe like invisible fault lines. And here's the tantalizing part, we might not need to wait centuries to find them. Quantum experiments are becoming sensitive enough to catch whispers of these hidden fields. If another scalar field exists, even weakly interacting, its subtle tremors could leave fingerprints in particle collisions or gravitational waves. It's like listening for footsteps in an empty house. The quieter the universe gets, the louder these ghosts of physics might become. The Higgs was just the beginning. Beyond it, an entire unseen architecture could be waiting, one that rewrites not just how particles get mass, but how reality itself holds together. Dark energy might be the universe's most frustrating mystery, an invisible force stretching space itself apart, yet we still don't know if it's even a constant. What if it's not just some static background energy, but something far stranger? A living, breathing field that evolves over time. This is the wild idea behind quintessence, a theory that suggests dark energy isn't a fixed number in the cosmos's equations but a dynamic player, waxing and waning like the tides of an unseen ocean. Picture a rubber band slowly losing its stretch, except this rubber band is space-time, and the tension controlling it could be changing in ways we can't yet predict. The evidence for this comes from subtle cracks in our cosmic models. If dark energy were truly constant, the universe's expansion should follow a smooth, predictable curve. But some observations hint at tiny deviations, as if the brakes on cosmic acceleration aren't fully set. Quintessence could explain these quirks. Unlike a static dark energy, this field would interact with itself and with matter, its strength fluctuating across billions of years. One moment it might surge, flinging galaxies apart faster. The next it could weaken, letting gravity claw back some control. It's a cosmic tug of war where the rope itself has a mind of its own. The implications are staggering. If quintessence is real, the fate of the universe might not be a slow, cold fade into darkness. Instead, the field could someday collapse entirely, triggering a catastrophic phase transition that rewrites the laws of physics overnight. Or it might spike violently, ripping apart galaxies, stars, even atoms in a final, big rip. But here's the twist, it could also reverse. Some models suggest quintessence might one day flip from repulsive to attractive, pulling the universe back together in a mirror of the Big Bang, a big crunch. Suddenly, dark energy isn't just a footnote in cosmology, it's the ultimate decider of reality's destiny. Yet the most tantalizing clue lies in the early universe. For a brief moment after the Big Bang, something eerily similar to quintessence called inflaton energy drove space to expand exponentially faster than light. Then, just as suddenly, it vanished. Could dark energy be inflaton's long-lost cousin, awakening after eons of dormancy? If so, we might be witnessing the opening act of a cosmic cycle we don't yet understand. The hunt for answers is already underway. Telescopes scan distant supernova for traces of changing expansion rates, while quantum physicists simulate how such a field might behave in the lab's smallest corners. Every flicker of data could be a breadcrumb leading us closer to the truth, because if dark energy is dynamic, then the universe isn't just expanding, it's alive, pulsing with hidden rhythms we're only beginning to hear. Among the most elusive candidates for dark matter, Axions whisper a possibility almost too elegant to ignore, particles so light and ghostly. They could flow through the cosmos like an invisible breeze, barely interacting with anything yet shaping galaxies with their collective weight. These hypothetical particles aren't just random guesses. They emerged from a puzzle at the heart of quantum physics. Why does the strong nuclear force, which glues atomic nuclei together, seem perfectly symmetrical in time? The math demanded an answer, and Axions were proposed as the universe's delicate fix, a cosmic correction so subtle, it spawned an entire hidden field. Picture a universe filled with an ethereal mist, one that doesn't clump like ordinary matter but ripples through space in vast, diffuse waves. That's the Axion field. Unlike heavier dark matter candidates, Axions would be billions of times lighter than electrons, meaning they'd behave less like particles and more like a pervasive hum in the fabric of reality. This could explain why dark matter refuses to crash into ordinary matter the way scientists expect. If Axions exist, they'd barely notice stars or planets. They'd simply phase through them, leaving only the faintest gravitational trace. But here's where it gets fascinating. Axions might not just be dark matter, they could reveal it. Under extreme conditions, like near a neutron star's crushing magnetic field, Axions might briefly glow, converting into detectable photons. It's as if the universe left a backdoor in its code, letting us catch glimpses of this shadowy substance. Experiments like ADMCS are already hunting for these telltale flickers inside ultra-sensitive magnetic chambers, tuning their detectors like cosmic radios searching for the right frequency. The implications stretch beyond dark matter. If the Axion field exists, it could solve another enigma: why the universe didn't self-destruct with equal amounts of matter and antimatter after the Big Bang. Tiny asymmetries in the Axion field's vibrations might have tipped the scales, favoring matter just enough to build everything we see. And then there's the wildest thought of all. Axions could be proof that the universe is more fluid than we realize. Some theories suggest the Axion field isn't static. It might oscillate across space and time, subtly altering fundamental constants in its wake. Imagine pockets of the cosmos where the laws of physics flex and shift, governed by the unseen ebb and flow of this phantom sea. We're standing at the edge of a revelation. Whether Axions are confirmed or not, their story forces us to rethink darkness not as an absence, but as a presence, an invisible architecture woven into the universe itself, waiting to be decoded. The inflaton field could be the universe's ultimate adrenaline rush, a surge of energy so powerful it stretched the cosmos from subatomic to astronomical size in less than a trillionth of a second. This wasn't just expansion, this was space itself unfurling faster than light, smoothing out wrinkles in reality like a cosmic iron pressing down on the fabric of existence. The idea of inflation solves some of cosmology's biggest puzzles: why the universe looks so uniform in all directions, why it's geometrically flat, and why we can't find any traces of those inevitable cosmic defects like magnetic monopoles. But the real mystery isn't just what happened, it's what caused it. Enter the inflaton field. Imagine it as a cosmic battery storing unimaginable energy in the early universe. For a fleeting moment, this field dominated everything, its pressure acting like anti-gravity, forcing space to balloon exponentially. Then, just as abruptly, it decayed, releasing its pent-up energy as a firestorm of particles, lighting the fuse for the Big Bang's afterglow. But here's the lingering question: did this field vanish entirely, or could remnants still linger, hidden in the vacuum of space? Some theories suggest the inflaton field didn't just disappear, it might have morphed. Like a waterfall feeding into a river, its energy could have cascaded into the fields we know today, including the Higgs. Others propose it's still out there, dormant, its energy diluted but not zero. If true, it might occasionally stir, causing subtle ripples in space-time or even triggering secondary bursts of inflation in distant pockets of the multiverse. The most tantalizing evidence comes from the cosmic microwave background, the afterglow of the Big Bang. Tiny fluctuations in this ancient light might carry fingerprints of the inflaton field's quantum jitters, stretched across the sky by inflation. Experiments like BICEP and the upcoming Lightbird mission are scanning these patterns for clues, hunting for primordial gravitational waves ripples that could only have been forged by inflation's violent expansion. But the wildest possibility, the inflaton field might not be unique. If multiple inflation events occurred, each driven by its own inflaton-like field, our universe could be just one bubble in a froth of endlessly inflating realities. Some of those bubbles might have entirely different laws of physics, shaped by how their own fields decayed. It's a dizzying thought. The same mechanism that forged our cosmos could have spawned countless others, each a separate experiment in reality. The search isn't just academic. If we can pin down the inflaton's properties, we might finally understand why our universe exists in this precise, life-friendly configuration, and whether it's a one-time accident or an inevitable outcome of deeper physics. The inflaton field didn't just shape space. It might have set the stage for every galaxy, star, and atom that followed. And if remnants still linger, they could be quietly shaping the cosmos even now, a ghostly handprint from the moment everything began. What if our universe is just a slice of something far larger, an invisible reality lurking beyond the edges of perception? String theory whispers this possibility, suggesting that we might be floating in a higher dimensional space like a sheet of paper suspended in a vast, unseen room. These hidden dimensions, often called the bulk, could be home to forces and fields that occasionally brush against our four-dimensional world, warping gravity, tweaking fundamental constants, or even offering a backdoor to other universes. Take gravity's puzzling weakness. In our universe, it's the feeblest of the fundamental forces, overpowered by electromagnetism a trillion times over. But what if gravity isn't weak, just diluted? Imagine a cup of water spilled on a table. From the perspective of an ant crawling on the surface, the water seems faint, barely there. But in reality, most of it has soaked into the table's depths. Similarly, gravity might appear weak because it's leaking into extra dimensions, its strength draining away into the bulk like water into porous wood. This brain-world scenario, where our universe is a membrane drifting in higher dimensional space, could explain why gravity feels so diffuse compared to other forces. The real kicker, these higher dimensions might not be empty. the bulk could be humming with its own hidden fields, cosmic currents that occasionally ripple into our reality. Some theories suggest dark matter might not be particles at all, but the gravitational shadow of massive objects moving in adjacent dimensions, like a ship's wake disturbing the surface of a calm sea. These unseen objects could tug on our universe's fabric, leaving behind the mysterious gravitational effects we attribute to dark matter. Even wilder is the idea that these bulk fields could bridge parallel universes. If another four-dimensional brain floated nearby in the bulk, fields stretching between them might allow energy or information to transfer, effectively creating a cosmic tunnel. It's a stretch, but not impossible. In fact, some models suggest that the Big Bang itself could have been triggered by a collision between our brain and another, unleashing the energy that birthed our cosmos. The hunt for evidence is already underway. Particle accelerators like the Large Hadron Collider search for tiny anomalies missing energy or unexpected particle behavior that might hint at gravity slipping into extra dimensions. Meanwhile, precision tests of gravity at microscopic scales look for deviations from Newton's laws, which could reveal hidden dimensions curled up smaller than an atom. But the most tantalizing clue might come from the cosmos itself. If higher dimensional fields exist, their influence could leave faint imprints on gravitational waves or the cosmic microwave background, subtle fingerprints waiting to be decoded. Whether these dimensions are compact, infinite, or warped beyond recognition, one thing's clear: reality might be far roomier than we ever imagined. What if dark energy isn't just a static force, but something that shifts and adapts, a cosmic chameleon blending into its surroundings? That's the radical idea behind the chameleon field, a hypothetical scalar field that doesn't play by fixed rules. Unlike the Higgs, which blankets the universe uniformly, this field would be sneaky. In the emptiness of space, it might stretch and push, driving galaxies apart. But near massive objects like stars or planets, it could shrink back, hiding its effects so well we'd never detect it locally. It's as if the universe has a secret dial for dark energy, one that twists depending on where you are. The math behind this is as elegant as it is bizarre. The chameleon field's strength wouldn't be constant, it would depend on the density of matter around it. Picture a shy creature in a crowded room. The more people squeeze in, the quieter it becomes, retreating into the background. But in an empty hall, it expands, filling the space with its presence. This behavior could solve one of dark energy's biggest puzzles: why its effects seem stronger in the voids between galaxies than near massive clusters. If the field's influence fades where matter is dense, it would neatly explain why we don't feel its push here on Earth, even as it accelerates the cosmos on the largest scales. Experiments are already hunting for this elusive field. By measuring tiny forces between objects in vacuum chambers, scientists hope to catch the chameleon's whisper, a slight, unexpected tug that betrays its presence. The stakes couldn't be higher. If the field exists, it wouldn't just explain dark energy, it could redefine how we think about gravity itself. Some models suggest the chameleon might mediate a fifth force, one that's been camouflaged all along in plain sight. But the wildest implication: this field could be a bridge between quantum weirdness and cosmic scale. Quantum fields usually operate on subatomic levels, yet here's one that might sculpt the entire universe, its behavior tuned by the environment like a grand cosmic feedback loop. It's a reminder that the laws of physics might not be rigid commandments, but flexible, dynamic rules shaped by the very space they govern. And if the chameleon field is real, it could mean dark energy isn't destined to tear the universe apart. Instead, its strength might evolve, ebbing and flowing with the cosmos's fate. One day, it could weaken, vanish, or even reverse, turning repulsion into attraction. The universe's end game might not be written in stone after all, but in the shifting, shimmering dance of a field we're only beginning to suspect. Imagine a force so relentless, it could tear atoms apart, shred space-time itself, and leave the universe as a cold, empty wasteland of isolated particles drifting hopelessly apart. This isn't a cosmic horror story. It's the chilling prediction of the phantom field, one of the most controversial theories in modern cosmology. Unlike dark energy, which accelerates the universe's expansion at a steady pace, the phantom field would grow stronger over time, its repulsive gravity snowballing until reality itself unravels in a cataclysmic Big Rip. What makes this field so terrifying is its behavior. Most fields weaken as the universe expands, their energy diluting across growing volumes of space. But the phantom field defies this logic. Its energy density increases with time, as if feeding on the very expansion it drives. Picture a car with an accelerator stuck to the floor, not just maintaining speed but relentlessly gaining velocity until the engine tears itself apart. That's the phantom field's grip on the cosmos, an inescapable feedback loop where each stretch of space fuels even faster stretching, accelerating toward oblivion. Not all physicists buy into this doomsday scenario. Critics argue that the phantom field violates fundamental energy conditions, creating negative kinetic energy, a concept that twists quantum field theory into knots. In simpler terms, it's like saying a river could flow uphill forever without any external push. Yet, some observations can't entirely rule it out. Measurements of distant supernova and galaxy clusters occasionally show anomalies consistent with an accelerating expansion rate that's not just steady, but increasing. The implications are staggering. If the phantom field exists, the universe's expiration date might not be billions of years away. It could happen in a cosmic blink. First, galaxies would be ripped from each other, then stars from their galaxies, planets from their stars. In the final moments, even atomic nuclei would be torn asunder, leaving behind a desolate sea of quarks and leptons, forever out of each other's reach. But here's the twist: the phantom field might not just be a death sentence. Some theorists suggest it could be a sign of deeper physics, a bridge to understanding how fields interact across multiple dimensions or how quantum gravity operates at cosmic scales. Others propose it's not a true field at all, but an illusion caused by our incomplete understanding of dark energy's true nature. One thing's certain: whether the phantom field is real or just a mathematical specter, it forces us to confront the fragility of reality. The universe might not fade quietly into darkness. It could end with a scream, a final, violent act written in the language of hidden fields we've only begun to decipher. Gravity is the force we know best and understand least. It pins us to the planet, guides the planets in their orbits, and bends the fabric of spacetime itself. Yet at the quantum level, it's a ghost. While the other fundamental forces have well-defined carriers, photons for electromagnetism, gluons for the strong force, gravity stubbornly resists this framework. Enter the graviton, the hypothetical particle that could finally bridge Einstein's relativity with quantum mechanics. If it exists, it wouldn't just be another particle. It would be a ripple in the graviton field, an invisible medium through which gravity's influence propagates across the universe. Picture dropping a pebble into a still pond. The ripples spread outward, carrying energy without the water itself moving far. In this analogy, the pond is the graviton field, and each ripple is a graviton, a tiny bundle of vibrational energy transmitting the force we experience as gravity. But here's the catch: gravitons would be unimaginably faint. Unlike photons, which can be detected with something as simple as your eyes, gravitons interact so weakly that a detector the size of Jupiter might catch just one per decade. This weakness isn't a flaw in the theory, it's a feature. Gravity's gentle pull compared to other forces makes perfect sense if its carrier particles barely stick to matter. The challenge of detecting gravitons isn't just technological, it's cosmic. To spot one directly, you'd need an instrument so sensitive it could measure disturbances smaller than a single quantum of spacetime itself. Even the most advanced gravitational wave detectors, like LIGO, rely on gravity's collective effect, the stretching of spacetime by massive objects like colliding black holes, not individual gravitons. It's like trying to hear a single note in a symphony by listening for the vibration of one violin string. Yet the graviton field's elusiveness might hide a deeper truth. Some theories suggest gravitons could be leaking into extra dimensions, their signal diluted across realities we can't perceive. Others propose that at ultra-high energies, like those just after the Big Bang, the graviton field might have interacted more strongly, leaving echoes in the cosmic microwave background. There's even a wild possibility that gravitons aren't particles at all, but emergent phenomena like waves in an ocean where the ocean itself is the true fabric of reality. The hunt continues. Experiments using ultra-cold atoms or precision measurements of orbiting satellites aim to catch gravity's quantum whispers. And if we ever confirm the graviton field's existence, it wouldn't just solve a puzzle, it would rewrite our understanding of reality's deepest layer. Gravity might be the weakest force, but its secrets could be the key to unlocking everything else. Neutrinos are the universe's ultimate ghosts, particles so elusive, trillions pass through your body every second without a trace. They barely interact with matter, slipping through planets like they're nothing but fog. Yet even these shadowy particles might be hiding something stranger, a secret gateway to an invisible neutrino field, one that could rewrite our understanding of physics. The clues lie in their eerie habit of shape-shifting, a phenomenon called neutrino oscillation. Picture a chameleon changing colors as it moves. That's what neutrinos do, flipping between three known types, electron, muon, and tau, as they travel. But here's the catch. The math behind these oscillations hints at a missing piece. To fully explain their behavior, some physicists suspect there's a fourth player, the sterile neutrino. Unlike its shy cousins, this phantom particle wouldn't even feel the weak nuclear force, the usual handshake between matter and neutrinos. Instead, it'd interact only through gravity, making it nearly undetectable except by the faintest tug on spacetime itself. Why believe in something so invisible? Deep underground, experiments like Mini-BU-NE and LSND have spotted odd flickers, more neutrino transformations than the three known types can explain. It's as if there's an extra door in the neutrino maze, one leading to a hidden room. If sterile neutrinos exist, they'd be born from a separate neutrino field entirely, a cosmic undercurrent humming beneath the reality we know. This field wouldn't just host particles, it might also hold the key to dark matter. Some theories suggest sterile neutrinos could be the elusive substance binding galaxies together, their collective gravity shaping the cosmos while remaining forever out of reach. The implications get wilder when you consider how this field might operate. If sterile neutrinos oscillate into regular ones, or vice versa, the process could release bursts of energy, heating the early universe or even seeding the supermassive black holes at galactic centers. Others propose these particles might be messengers from extra dimensions, their strange behavior a ripple from realms beyond our perception, yet the most tantalizing idea. This field could be a bridge between quantum mechanics and gravity. If sterile neutrinos truly feel only gravity, they might carry clues about how spacetime behaves at the smallest scales, a puzzle that stumped physicists for a century. Experiments like the upcoming Dune project aim to chase these phantoms, using colossal detectors filled with liquid argon to catch the subtlest neutrino whispers. Every flicker of data could rewrite the rules, because if sterile neutrinos are real, they're not just oddball particles, they're shadows of a hidden layer of reality, one where gravity, dark matter, and the quantum world collide. The universe's quietest particles might be its loudest messengers. We just have to learn how to listen. Magnets are everywhere, holding notes on fridges, guiding compass needles, even lurking in your smartphone. But here's something strange. Every magnet we've ever found has two poles, a north and a south. Snap one in half and you don't get isolated poles, you just get two smaller dipoles. It's as if the universe refuses to let magnetic charges exist alone. Or does it? Buried in the equations of quantum physics is a tantalizing possibility. magnetic monopoles, hypothetical particles carrying just a single pole, like an electric charge but for magnetism. If they're real, they'd rewrite the textbooks and hint at a hidden field threading through the cosmos. The hunt for monopoles isn't just about symmetry. Electrically, the universe is perfectly happy with solo charges. Protons and electrons exist independently. But magnetism seems locked in pairs, a quirk that's bothered physicists since Maxwell's time. Dirac took it further, showing that if even one magnetic monopole exists anywhere in the universe, it would explain why electric charge comes in neat, discrete packets. It's like finding a single torn dollar bill and realizing it proves all currency must be printed in whole denominations. Where would these phantom particles come from? The leading theory points to the early universe's chaos. During the Big Bang, as fundamental forces split from their primordial unity, spacetime might have crystallized with defects, cosmic knots where the magnetic field lines snap into isolated points. These would be monopoles, relics of a phase transition more extreme than any superconductor's shift. Some models suggest they'd be monstrously heavy, possibly even primordial black holes in disguise, carrying magnetic charge instead of mass. The wildest implication, monopoles wouldn't just be particles, they'd be proof of a hidden magnetic field structure governing reality. Ordinary magnetism arises from moving electric charges, but monopoles would demand their own independent field, one that doesn't rely on electricity at all. This field could permeate the universe like the Higgs, subtly influencing particle behavior in ways we've never noticed. So why haven't we found any? Experimentalists have turned everything from moon rocks to ancient mica into monopole detectors, scouring for traces of these elusive particles. Theoretically, inflation might have diluted them to near non-existence, stretching space so thin that only a handful survive in our entire observable universe. Or they could be hiding in plain sight, masquerading as dark matter or lurking in the hearts of neutron stars, their magnetic charge balanced by dense plasma. The search isn't over. Giant underground labs like Mo Edel hunt for monopoles by watching for their unique ionization trails, while cosmological surveys probe the early universe for clues. If we ever spot one, it won't just fill a gap in the equations, it'll crack open a door to a deeper layer of reality, where fields we've never seen sculpt the forces we take for granted. The universe's magnetic secret might still be out there, waiting for the right experiment to pull it into the light. Einstein gave us gravity as the curvature of spacetime, but what if that's only half the story? Hidden in the equations of general relativity lies a forgotten player, torsion, a twisting of spacetime's fabric so subtle we've overlooked it for a century. Picture a rolled-up carpet. Einstein's gravity bends it like a weight pressing down, but torsion would be the unseen twist in its fibers, a spiral distortion running through the very threads of reality. Most models set torsion to 0 for simplicity, but some physicists suspect this geometric ghost might hold answers to cosmology's biggest gaps. Unlike curvature, which warps space around mass, torsion could emerge from the intrinsic spin of particles themselves. Every electron, quark, and neutrino spins like a tiny top, and if these rotations collectively twist spacetime at microscopic scales, the effects might cascade upward. Think of a million spinning tops on a stretched rubber sheet. Their combined motion might not just dent the surface, but corkscrew it in ways we've never measured. This isn't just abstraction. Certain unified theories, like Einstein-Cartan gravity, naturally include torsion as a partner to curvature, with the potential to reshape how we understand everything from black holes to cosmic expansion. The most tantalizing possibility, torsion could be masquerading as dark energy. If spacetime's twist interacts with quantum fields in just the right way, it might generate a repulsive effect, pushing galaxies apart without any phantom energy required. It's like a coiled spring hidden in the vacuum of space, its tension driving expansion from within the geometry itself. Others propose torsion might soften gravity's grip on large scales, mimicking modified gravity theories without invoking unseen particles. But how would we detect such an elusive effect? Torsion wouldn't just bend light like curvature, it'd rotate it, subtly twisting the polarization of starlight as it travels through space. Experiments hunting for cosmic birefringence, like those analyzing the cosmic microwave background, could stumble upon its fingerprints. There's also a wild card. If torsion couples strongly to particle spin, ultra-precise quantum sensors might catch atoms wobbling in unexpected ways, their spins tugged by spacetime's hidden helices. Yet the boldest idea is that torsion could bridge quantum mechanics and gravity. In extreme environments like the singularity inside a black hole, torsion might prevent infinite curvature, acting as nature's geometric fuse to stop spacetime from tearing itself apart. If true, this forgotten field isn't just a curiosity. It's a cosmic stabilizer woven into the universe's blueprint to keep reality from unraveling at the seams. The math is elegant, the implications profound, but for now, torsion remains a whisper in the equations. Whether it's a minor correction or a key to the cosmos's deepest secrets, one thing's clear: spacetime might be far more dynamic than we ever dreamed. Not just bent but twisted, not just a stage but a dancer, and if we learn to see its spirals, we might finally decode the universe's hidden choreography. Empty space isn't empty, it's a seething ocean of infinite energy bubbling beneath the surface of reality. This is the zero-point field, the quantum vacuum's restless hum, where particles flicker in and out of existence so fast they barely leave a trace. Unlike ordinary energy, this isn't something you can ever shut off. Even at absolute zero, when all motion should cease, the field keeps vibrating, a cosmic drumbeat that never fades. The numbers are staggering. A single cubic centimeter of empty space could contain more zero-point energy than all the matter in the observable universe combined. Yet here's the paradox: we can't touch it. It's like standing knee-deep in a river of molten gold, only to find it slips through your fingers every time you try to scoop it up. The zero-point field isn't just theoretical noise. We've seen its fingerprints in the lab. Take the Casimir effect, where two metal plates in a vacuum inexplicably pull together. That's zero-point energy at work. The plates exclude certain quantum fluctuations, creating an imbalance that nudges them inward. Or consider the Lamb shift, where electrons in hydrogen atoms wobble slightly off their predicted orbits, jostled by the vacuum's relentless buzz. These aren't quirks, they're proof that the universe's baseline isn't stillness, it's chaos, a froth of potential waiting to be tapped. But could we ever harness it? The dream of zero-point energy has fueled everything from sci-fi warp drives to conspiracy-laden, free energy claims. The reality is far thornier. Quantum fields don't lend themselves to easy extraction, like trying to bottle lightning from a storm that exists everywhere at once. Some theories suggest manipulating spacetime itself, using engineered materials or exotic configurations to siphon vacuum energy. Imagine a sponge squeezed in just the right way to wring out a few drops. NASA Eagleworks lab even experimented with ideas like the M-drive, a controversial thruster that some claimed might tap into these quantum ripples, though results remain hotly debated. The wildest possibility, the zero-point field might not just be energy, it could be the substrate of reality itself. Some interpretations of quantum mechanics suggest particles aren't tiny marbles, but knots of excitation in this underlying field, like whirlpools in an invisible river. If true, mastering the field wouldn't just mean unlimited power, it'd mean rewriting the rules of existence. Want to teleport an object, twist the field in just the right way, and matter might leap across space without crossing the distance in between. Dream of faster-than-light travel, ride the zero-point waves like a surfer catching a cosmic tide. Yet the universe guards its secrets fiercely. Every attempt to extract zero-point energy runs into the same wall, The energy is there, but it's perfectly balanced, cancelling itself out unless disturbed in ways we don't yet understand. Some physicists argue that even if we could tap it, the consequences might be catastrophic, unleashing vacuum decay, where a single misstep could trigger a domino effect, rewriting the laws of physics across the cosmos. For now, the zero-point field remains the ultimate tease, infinite energy, locked behind a door with no handle, but the search continues. Quantum physicists probe its edges, engineers dream of cracking its code, and the universe hums along, keeping its most volatile secret just out of reach. One thing's certain, if we ever learn to dance with this invisible force, humanity won't just reach the stars, we'll rewrite the very fabric of the journey. What if everything you see, the stars, the planets, even your own hands, is nothing more than an illusion, a cosmic mirage projected from the edges of reality? This isn't science fiction. It's the holographic principle, a mind-bending theory suggesting our three-dimensional universe might be a shadow cast by information etched onto a distant two-dimensional surface. Think of it like a movie screen. The images appear lifelike, full of depth and motion, but peel back the illusion and you'll find their true source, flat, flickering pixels. According to this idea, the universe works the same way. Every event, every particle, every law of physics could just be data encoded on a hidden boundary we'll never see. The roots of this theory lie in black holes. When an object falls into one, it vanishes from our universe, but its information can't just disappear. Quantum mechanics insists on that. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, a measure of its hidden information, is proportional not to its volume but to its surface area. It's as if all the data about what fell in gets compressed onto the event horizon, like a cosmic hard drive. Decades later, string theorists like Leonard Susskind took this further, proposing that the entire universe might operate the same way. If a black hole's interior can be described by information on its boundary, why not everything else? The implications are staggering. If the holographic principle holds, the universe isn't just containing information, it is information. The chair you're sitting on, the air you're breathing, even your thoughts could be fragments of a vast, interconnected code written on the fabric of spacetime. This would mean our perception of three dimensions is a kind of cosmic sleight of hand, with the true workings of reality happening on a distant, flat plane we can't access. It's like living inside a video game, unaware that the textures, physics, and even time itself are just rendered from a deeper layer of algorithms. But how could this possibly work? The math points to something called ad-SCFT duality, a theoretical bridge between gravity in 3 dimensions and quantum fields in 2. In simpler terms, it suggests that a universe with gravity, like ours, could be perfectly mirrored by a lower dimensional system without gravity at all. Picture a snow globe. The intricate winter scene inside seems real, but it's wholly defined by the glass sphere enclosing it. Now imagine that sphere isn't just reflecting the scene, it's generating it pixel by pixel from its surface. The real test lies in the fine print of reality. If the universe is holographic, there should be limits to how much information any given space can hold, a cosmic resolution limit. Some scientists are hunting for these pixelation effects in the faintest light from distant quasars or the quantum jitter of spacetime itself. Others are simulating holographic universes in supercomputers, watching to see if 3-dimensional physics truly emerges from 2-dimensional rules. Yet the wildest question isn't how, it's why. If the holographic principle is true, who or what is the projector? Is this hidden field a natural structure like the universe's own operating system? Or could it hint at something even stranger, that our reality is a constructed artifact, a simulation running on hardware we'll never see? The answers might lie beyond our current physics, in a realm where information isn't just a tool for understanding the universe, but the very stuff from which it's made. One thing's certain, if the holographic principle is real, we're not just observers of the cosmos. We're participants in an illusion so vast, we're only now beginning to suspect the curtain exists. And behind it, the universe's deepest secrets might not be written in stars or atoms, but in bits ancient, immutable, and waiting to be decoded. Time might feel like the most constant force in our lives, always ticking forward, never bending to our whims. But what if that's just an illusion? What if time isn't a rigid arrow but a fluid current shaped by a hidden field, one we could theoretically tap into, twist, or even reverse? Enter the chronon field, a speculative idea that suggests time itself could be governed by an invisible cosmic framework, just like gravity or electromagnetism. Think of it like this: space is flexible. We know that from general relativity, where massive objects bend it like a trampoline. So why should time be any different? If the chronon field exists, it might stretch, compress, or ripple under certain conditions, altering how fast clocks tick or even allowing information to loop back on itself. Imagine a river where the current isn't fixed. Sometimes it rushes, sometimes it eddies, and in rare cases, it might even swirl backward. That's the kind of control the chronon field could exert over time's flow. The tantalizing part: we've already seen hints that time isn't as uniform as it seems. Atomic clocks on GPS satellites tick faster than those on Earth, proof that gravity and velocity tweak time's passage. And in quantum mechanics, particles like electrons don't seem to care about time's direction at all, behaving the same whether time flows forward or backward. Could these anomalies be glimpses of the chronon field's subtle influence? Time travel, of course, is the elephant in the room. If this field can be manipulated, the rules change entirely. Wormholes, often theorized as shortcuts through space-time, might not just bend space but tap into the chronon field's currents, creating loops where cause and effect blur. Some models suggest extreme rotations, like those near a spinning black hole, could twist the field enough to form closed time-like curves, paths where you end up back where you started, not just in space but in time. But here's the catch: the chronon field wouldn't be easy to harness. It might require energy densities beyond anything we can produce, or exist only in conditions so extreme, like the singularity inside a black hole, that accessing it borders on fantasy. Even worse, meddling with time could trigger paradoxes that unravel causality itself. It's like pulling a thread on a sweater. Tug too hard, and the entire fabric of reality might unravel. Yet the implications stretch far beyond time machines. If the chronon field is real, it could explain why time has a direction at all. The arrow of time, the fact that we remember the past but not the future, might stem from this field's default settings, a kind of cosmic bias written into the universe's code. Dark energy's acceleration of the universe, maybe it's not just stretching space but stretching time's fabric too, thinning it out like taffy pulled to its limit. The search for evidence is already underway. Quantum physicists are designing experiments to test whether time truly flows at the smallest scales or if it's an emergent property of deeper physics. Cosmologists scour the cosmic microwave background for anomalies that might reveal time's hidden structure. Even artificial intelligence gets in on the act, simulating universes with alternate time laws to see which ones hold together. Whether the chronon field is a revolutionary truth or a beautiful mirage, one thing's certain: time isn't as simple as it seems. It might not be a backdrop to the universe, but a player, a dynamic, malleable force waiting for us to decode its secrets. And if we ever do, the future won't just be something we move toward. It could be something we shape. The notion of the ether was once science's most infamous dead end, an invisible medium thought to fill space like an ocean of light, only to be tossed aside when Einstein proved it unnecessary. But what if we dismissed it too soon? Quantum physics has a way of resurrecting old ghosts, and the ether might be due for a comeback, not as the rigid, mechanical fabric of 19th-century dreams, but as something far stranger. Picture the luminiferous ether as Victorian scientists imagined it, a motionless, all-pervading substance through which light waves traveled like ripples in a pond. When Michelson and Morley failed to detect Earth's motion through this supposed medium, the idea crumbled until quantum field theory gave it new form. Today's vacuum isn't empty, it's a frothing quantum foam where fields buzz with latent energy. In a way, the modern Higgs field is a kind of ether, a cosmic molasses giving particles mass. But could other, subtler fields linger like echoes of that old idea? Some theorists suggest the quantum vacuum itself might qualify as an ether reborn. Empty space teams with virtual particles flickering in and out of existence, their fleeting presence governed by fields that permeate everything. This isn't the static backdrop of the past, it's a dynamic, seething substrate that bends to quantum rules. Even light doesn't strictly need a medium to travel, but it does interact with these fields, its behavior subtly shaped by the vacuum's hidden structure. The implications get wilder when you consider gravity. Einstein's space-time curvature replaced the ether as gravity's explanation, but what if curvature is just one piece of the puzzle? Modified gravity theories sometimes invoke an underlying field to explain anomalies like dark matter's pull. This wouldn't be the rigid ether of old, but a flexible, responsive framework that guides spacetime's shape rather than resisting it. Think of it like the difference between a wooden stage and a trampoline. One simply sits there while the other actively shapes every movement upon it. Here's where the real twist lies. If the ether is reimagined as a quantum field, or a network of them, it might solve lingering gaps in physics. Dark energy's repulsive force could stem from this underlying framework's tension, like a stretched rubber sheet pushing outward. Or quantum entanglement's spooky action at a distance might rely on hidden connections woven through the vacuum itself, making the ether not a medium for motion but for information. The irony is delicious. Our idea once banished for being too clunky might return as something utterly elegant, not a substance, but a symphony of interacting fields, their harmonies dictating the universe's deepest rhythms. Whether we call it ether or something new, the lesson is clear. Sometimes science doesn't discard its old models, it transcends them, and in the quantum age, even history's misfits might get a second act. Consciousness might be the greatest unsolved mystery in science, an inner world of thoughts, feelings, and awareness that somehow emerges from silent neurons firing inside a 3-pound lump of tissue. But what if the brain isn't generating consciousness at all? What if it's more like a radio tuning into a signal broadcast by something far stranger, a hidden field woven into the fabric of reality itself? This is the radical idea behind the consciousness field, a theory that flips neuroscience on its head by suggesting our minds aren't confined to our skulls, but linked to a cosmic network older than stars. The clues start with the hard problem of consciousness, the puzzle of why subjective experience exists at all. Brains process information, but why should that feel like anything? Why aren't we just biological robots churning through inputs without a flicker of inner light? Some theorists argue that no amount of neuron mapping will ever solve this because consciousness isn't purely physical. Instead, it might be fundamental, like space or time, a property the universe is built to express. Enter the consciousness field. Picture it like an invisible ocean, its waves resonating with every thought, memory, and sensation. Your brain wouldn't create awareness, it would filter it, shaping raw experience into the coherent stream we recognize as self. This isn't just philosophy. Quantum biology hints that microtubules inside neurons might interact with quantum fields in ways we don't yet understand. Experiments with psychedelics add fuel to the fire. When people report ego dissolution or mystical unity with the cosmos, could they be briefly tuning into this field's unfiltered signal? The implications are staggering. Near-death experiences, vivid recollections of tunnels, lights, and floating outside one's body, might not be hallucinations, but moments when the brain's receiver malfunctions, picking up interference from the broader field. Even collective consciousness phenomena like hundredth monkey effects or shared intuition in twins separated at birth could stem from this underlying connectivity. But the wildest idea, the field might not be static. Some theories propose it evolves, learning from every conscious being that taps into it. Imagine a universe that grows more self-aware as life flourishes within it, a cosmic feedback loop where consciousness shapes reality as much as reality shapes consciousness. It's a modern spin on ancient ideas, from Buddhist mind-only philosophies to panpsychism's claim that even atoms have a whisper of experience. Skeptics, of course, demand proof. If the consciousness field exists, where's the detector that can measure it? Efforts like the Global Consciousness Project aim to find out, tracking random number generators for statistical anomalies during global events, moments when collective focus might ripple through the field. Others suggest we're simply looking in the wrong place. The field's effects might be too subtle for current tools, hidden in quantum decoherence or the mysterious collapse of the wave function. Yet, even if the theory remains unproven, it forces us to confront a profound possibility, that the universe isn't just aware because of us, but that we're aware because of it. The mind might not be a prisoner of the brain, but a traveler dancing between neurons and the infinite, forever tethered to a mystery deeper than physics itself. All living things glow not with the warm radiance of fireflies or bioluminescent algae, but with an invisible light so faint you'd need the most sensitive instruments to catch even a whisper of it. These ultraweak emissions, called biophotons, aren't just random noise. They pulse in patterns, flickering in sync with cellular processes, as if our bodies are quietly humming with a hidden symphony of light. Some researchers believe this isn't just a biological quirk. It's evidence of a deeper, more mysterious connection between life and the quantum world. Picture a single cell dividing. As chromosomes align and proteins fold, molecules release photons, tiny sparks in the darkness. Under normal circumstances, this glow is drowned out by the chaos of metabolism. But in controlled studies, scientists have found something startling. These photons aren't entirely random. They appear coordinated, sometimes even oscillating in unison across tissues. It's as though cells aren't just producing light, but communicating with it, sending signals through a medium we're only beginning to perceive. The implications flirt with the edges of science fiction. Could living organisms be entangled in a biophoton field, a web of light connecting cells, organs, even entire ecosystems? Experiments with plants lend eerie support to the idea. When two seedlings are grown side by side, then separated by an opaque barrier, their photon emissions sometimes remain synchronized, as if still talking across distances no known chemical signal could bridge. Even more perplexing, damaged cells emit bursts of biophotons that seem to trigger repair responses in healthy neighbors, hinting at a form of light-based healing we don't yet understand. But how deep does the rabbit hole go? Quantum biology suggests our cells might exploit phenomena like entanglement and coherence, the same rules governing particles in a lab. If true, the biophoton field could be the missing link, a bridge between the deterministic world of biology and the probabilistic realm of quantum mechanics. Enzymes might use photons to test chemical pathways before committing, or neurons could sync firing patterns via light pulses faster than electrical signals could travel. Skeptics, of course, demand ironclad proof. The biophoton field remains controversial, its effects often dismissed as experimental artifacts or statistical anomalies. Yet the whispers persist, in the way wound healing accelerates under certain wavelengths of light, or how meditators exhibit altered biophoton emissions, as if consciousness itself tweaks the dial on this hidden channel. Whether the biophoton field is real or just a beautiful hypothesis, it forces us to reconsider life's most basic processes. If light truly weaves through our cells, linking mind, body, and environment in ways we've yet to map, then biology isn't just chemistry, it's something far stranger, dancing at the edge of the visible and the imagined. And we might be standing at the threshold of a new science, one where healing, communication, and even thought pulse not in silence but in light. At the smallest scales imaginable, far smaller than atoms, even smaller than quarks and electrons, the universe stops making sense. The smooth spacetime Einstein described in his equations becomes a chaotic foam, churning with quantum fluctuations so violent they twist reality into knots. This is the Planck scale, where distances shrink to a trillionth of a trillionth of a trillionth of a meter, and time ticks in fragments too brief for any clock to measure. Here, gravity doesn't just bend space-time, it shatters it, leaving behind a seething ocean of virtual black holes, wormholes, and bridges to other dimensions. And if physicists are right, this frenzied underworld might be governed by something even stranger: the Planck field, a hidden scaffold stitching reality together at its most fundamental level. Think of it like this: if space-time were a sheet of glass, the Planck scale would reveal it's not smooth at all, but a mosaic of microscopic cracks and fractures. The Planck field would be the glue holding those fragments in place, dictating how they shift and rearrange as the universe evolves. Unlike the Higgs field, which gives particles mass, or the electromagnetic field, which carries light, this field wouldn't just influence matter, it would define the very arena in which matter exists. Without it, space-time itself might dissolve into meaningless static, like a TV screen losing its signal. The implications are staggering. If the Planck field exists, it could be the missing link between quantum mechanics and gravity, two theories that have stubbornly refused to reconcile for a century. At normal scales, gravity behaves predictably, warping space-time in smooth curves. But zoom into the Planck level, and those curves turn into jagged, fractal edges where the concept of here and now blurs into uncertainty. The Planck field might smooth out these quantum tremors, acting as a mediator that keeps spacetime from unraveling entirely. Some models even suggest that particles and forces aren't separate entities at this scale, but vibrations of the same underlying field, like different notes played on a single cosmic string. But how would we ever detect such an elusive force? Direct observation is impossible with current technology. The Planck scale is a realm of energies quadrillions of times beyond what our most powerful particle colliders can reach. Yet nature might have left us clues. The afterglow of the Big Bang, the cosmic microwave background, could carry faint imprints of the Planck field's quantum jitters stretched across the sky by inflation. Gravitational wave detectors like LIGO might one day catch echoes of microscopic black holes popping in and out of existence, their brief lives governed by this field's rules. Even the mysterious holographic noise some theorists predict, a faint fuzziness in the vacuum, could be the Planck field's fingerprint, a whisper from the universe's deepest layer. The wildest possibility, the Planck field might not just be a passive framework, but an active player in cosmic evolution. Some theories propose that in the extreme conditions of the early universe, fluctuations in this field could have seeded the first structures, tiny quantum knots that snowballed into galaxies and galaxy clusters. It's a cosmic version of the butterfly effect, infinitesimal tremors at the Planck scale swelling into the vast architecture of the cosmos. And if we ever learn to manipulate this field, the applications would dwarf science fiction. Warp drives, stable wormholes, even tweaking the fundamental constants of reality, all might hinge on understanding how the Planck field weaves the fabric of existence. Of course, that's a big if. For now, the Planck field remains a tantalizing ghost in the equations, a shadow of a theory waiting for its moment in the light. But one thing's certain: if this hidden architect of reality is real, the universe is far stranger and far more intricate than we ever dared to dream. Quantum entanglement is one of the most baffling phenomena in physics, two particles linked in such a way that changing the state of one instantly influences the other, no matter how far apart they are. Einstein called it spooky action at a distance, a phrase that perfectly captures how unsettling it feels to our classical intuition. But what if this isn't just a weird quirk of quantum mechanics? What if entangled particles are whispering to each other through a hidden network, an entanglement field that binds them together across the vast emptiness of space? Imagine tossing two coins into opposite ends of the universe. In our everyday experience, flipping one coin shouldn't affect the other, but with entanglement, the moment one lands on heads, the other must land on tails. No delay, no signal, just instantaneous correlation. The strangeness isn't just in the outcome, it's in the sheer immediacy of the connection. No signal can travel faster than light, yet entangled particles seem to bypass that rule entirely, as if they're not truly separate but nodes in a deeper, invisible web. That's where the entanglement field comes in, a hypothetical medium that doesn't transmit information the way light or gravity does, but instead maintains an unbreakable, non-local link between particles, like marionettes controlled by the same hidden strings. Quantum mechanics doesn't explain how entanglement works, it just tells us that it does. The equations predict perfect correlations, but they're silent on the mechanism. Some interpretations, like the pilot wave theory, suggest particles are guided by a hidden layer of reality, a kind of quantum ether that orchestrates their behavior. Others propose that the entanglement field isn't a physical medium but a fundamental feature of the universe's geometry, where space and time are secondary to a deeper, more abstract connectedness. It's like two people on opposite sides of the world, both dreaming the same dream, separate, yet inexplicably synchronized without any direct contact. The implications go far beyond lab experiments. If the entanglement field exists, it could rewrite our understanding of space itself. Normally, distance dictates interaction, gravity weakens, signals fade, but entanglement doesn't care about distance. That suggests space might not be the ultimate arena of reality, just a surface layer draped over something far more interconnected. Think of it like a hologram. What appears as empty space to us could be seething with invisible threads tying everything together. Some theories even suggest that black holes, those cosmic shredders of information, might preserve data through entanglement, encoding it in a field that survives their destruction. Yet the biggest question remains, could we ever harness this field? Quantum computing already exploits entanglement to perform calculations impossible for classical machines, but if the field is real, the potential goes further. Secure communication networks that defy eavesdropping, sensors that detect disturbances in the field itself, even speculative ideas like entanglement-based teleportation of quantum states all hinge on understanding this invisible web. The catch: we'd need to prove the field exists first. Right now, entanglement is a correlation we observe, not a force we can measure. Experiments are inching closer. Tests of Bell's inequality have ruled out local hidden variables, pushing us toward non-local explanations. Some physicists are probing whether entanglement leaves faint imprints in the vacuum, like ripples in a pond. Others are simulating quantum fields in ultra-cold atoms, searching for patterns that might mirror the entanglement field structure. Every flicker of data brings us closer to answering whether spooky action is just a metaphor or the first clue to a hidden dimension of reality, one where distance is an illusion and everything is far more connected than it seems. Even in the quietest corners of the universe, where no stars shine and no particles stir, quantum fields hum with an energy we can't perceive. This baseline hum is called the vacuum expectation value, and it's not just background noise. It's the universe's hidden foundation, the silent anchor that shapes everything from the mass of particles to the very laws of physics. But what if this anchor isn't constant? What if it shifts like sand beneath our feet, creating invisible fault lines where the rules themselves bend? Picture the vacuum expectation value as the universe's default setting. The energy level quantum fields settle into when left undisturbed. The Higgs field is the most famous example. Its vacuum expectation value gives particles mass, like an invisible tide lifting some higher than others. But here's the twist. In theory, there's no law demanding this default be uniform. Some regions of space could have higher or lower values, like valleys and peaks in an unseen landscape. These fluctuations wouldn't just tweak particle properties, they could rewrite physics locally, creating pockets where forces behave differently or even where matter itself becomes unstable. The wildest implication, these shifts might not be random. Cosmic strings, hypothetical defects in spacetime's fabric, could mark boundaries where vacuum expectation values change abruptly. Imagine stepping over an invisible line and suddenly electrons weigh twice as much, or the speed of light slows by a fraction. Such cosmic phase transitions might have occurred in the early universe, leaving behind relic domains where the laws of physics are subtly or dramatically different. We're not just speculating. Variations in vacuum expectation values could explain eerie anomalies like the Hubble tension, where measurements of cosmic expansion refuse to agree. If certain regions of space have lower vacuum energy, they'd expand slower, throwing off our calculations. Dark energy's mysterious effects might also trace back to this field's uneven terrain, with its repulsive force waxing and waning across the cosmos like a tide we can't see. Yet the boldest idea is this: the vacuum expectation value might not be set in stone. Some theories suggest it could evolve over cosmic timescales, inching toward a new equilibrium. If that happens, the universe as we know it could unravel in a catastrophic vacuum decay, where a bubble of true vacuum expands at light speed, rewriting physics in its wake. One moment, atoms hold together, the next they dissolve into raw energy. For now, we're left with tantalizing hints. Particle colliders hunt for signs of metastable vacua, while astronomers map the cosmos for statistical wrinkles that betray hidden asymmetries. Whether this field varies or not, one thing's clear: the universe's quietest hum might be its most powerful voice, and we're only just learning how to listen. Galaxies don't just drift randomly through the cosmos, they move with purpose, pulled by gravity's invisible hand. But something's off. When astronomers mapped the motion of thousands of galaxy clusters, they found an eerie pattern. A vast river of galaxies all streaming in the same direction, as if tugged by something beyond the edge of our observable universe. This isn't just gravity as we know it. This is the dark flow, a cosmic current so vast and unexplained it hints at forces or fields operating on scales we can't yet see. Picture the universe as a chessboard. Most pieces move predictably, governed by the visible board, but what if something outside the board is nudging them? That's the unsettling implication of dark flow. Galaxy clusters weighing trillions of suns are drifting toward a single patch of sky at speeds over 2 million miles per hour faster than the expansion of space alone can explain. The strangest part, the direction doesn't align with any known supercluster or void. It points toward nothing, or rather, nothing we can detect, the leading theory. A hidden field, one that stretches beyond our cosmic horizon. Just as the Higgs field permeates space to give particles mass, this dark flow field might exert a gentle but persistent pull on entire galaxies. Some models suggest it could be the gravitational shadow of another universe brushing against ours in the multiverse foam, its influence leaking through like magnetism through a wall. Others propose it's a relic of the pre-Big Bang era, a cosmic fossil imprinted on spacetime during inflation when the universe ballooned faster than light. Then there's the radical possibility that dark flow isn't a field at all, but a wrinkle in spacetime itself. If the early universe wasn't perfectly uniform, if some regions stretched more than others, it could have left behind a gravitational slope, tilting galaxies toward a deeper well we can't see. Think of it like water swirling down a drain, except the drain exists outside our observable bubble, in a realm of space and time forever hidden from view. The hunt for answers is pushing telescopes to their limits. Projects like the eROSITA X-ray survey are mapping galaxy motions in unprecedented detail, while simulations recreate the birth of cosmic structures to see if dark flow emerges naturally or demands new physics. Every data point tightens the noose around this mystery, because if dark flow is real, it's not just a curiosity. It's a crack in the facade of our universe, a hint that reality extends far beyond what we'll ever see. And whatever's out there, it's pulling us toward a revelation we're not yet ready to comprehend. What if the Big Bang wasn't the beginning, just the latest reboot in an endless cycle of cosmic destruction and rebirth? This is the startling premise of the ekpyrotic universe, a model where our entire cosmos is caught in an eternal loop, each iteration triggered by a hidden force, the ekpyrotic field. Unlike traditional Big Bang theory, which starts with a singularity, this idea suggests our universe was born from something far stranger, a collision between two higher dimensional membranes or branes, floating like sheets of paper in a vast, unseen bulk. And the force behind these cataclysmic crashes, an invisible field pulsing through the fabric of reality, drawing these branes together over eons until, boom, they collide, unleashing enough energy to forge a new universe from the ashes of the old. Picture two sheets of paper drifting toward each other in a silent room. Now imagine those sheets are entire universes, separated by a gap so tiny, it's curled up in dimensions we can't perceive. The ekpyrotic field is the hand pushing them together, its tension building until contact is inevitable. When they meet, the impact doesn't just spark a fireball, it resets the cosmic clock, scattering matter and energy in a way that perfectly mimics the conditions we call the Big Bang. It's like hitting a cosmic reset button where each cycle inherits the remnants of the last, but with subtle variations. This could explain why our universe seems so finely tuned for life. After countless iterations, the parameters have settled into a sweet spot, like dice eventually landing on the perfect roll. But the ekpyrotic field isn't just a wrecking ball, it's also a sculptor. In the eons between collisions, this field stretches and smooths the branes, ironing out wrinkles and erasing imperfections. That's why our universe appears so uniform, with no traces of the chaos that might follow a collision. The field's gentle tug ensures that when the branes finally crash, they do so cleanly, like two panes of glass sliding into place, leaving behind a cosmos that's pristine and ready for a fresh start. The implications rewrite cosmic history. Instead of a singular, incomprehensible beginning, time becomes a wheel, turning endlessly through phases of expansion, collision, and renewal. Dark energies accelerating expansion, just the ekpyrotic field pulling the branes apart after their last encounter, priming them for the next, the cosmic microwave background's faint patterns. Echoes of perturbations from previous cycles, stretched thin but never entirely erased. Even black holes might not be eternal. They could dissolve during each collision, their information encoded in the brane's vibrations, only to re-emerge in the next universe like data on a recycled hard drive. Critics argue that the model trades one mystery for another, replacing the Big Bang's singularity with an unobserved higher dimensional ballet. Yet the theory has surprising resilience. It sidesteps the initial conditions problem plaguing standard cosmology, where the universe's improbable fine-tuning demands explanation. And unlike inflationary models, which struggle to explain certain large-scale structures, the ekpyrotic scenario naturally predicts a smoother, more uniform cosmos, thanks to the field's relentless smoothing effect. The search for evidence is a race against time, literally. If our universe emerged from a brane collision, gravitational waves from that event would have been stretched to impossibly long wavelengths by now, far beyond our detector's reach. But there's hope. Certain signatures might linger in the polarization of the cosmic microwave background, subtle swirls that telescopes like Light-Bird or future space observatories could uncover. Others suggest hunting for cosmic strings, defects in spacetime that could have formed as the branes ripped apart during collision, leaving behind scars that even time can't heal. Whether the ekpyrotic field is real or just a beautiful hypothesis, it forces us to confront a dizzying possibility. Our universe might not be a one-and-done event, but a single frame in an infinite cosmic film strip. And if the cycle holds, the next collision could already be looming in the unseen depths of the bulk, a ticking clock counting down to the universe's next rebirth. The early universe was a place of perfect symmetry, a hot, dense soup where all forces were one, all particles identical, and the very fabric of reality was uniform. But today's cosmos is anything but symmetrical. Forces have split, particles have gained mass, and empty space teems with complexity. What shattered this primordial perfection? The answer might lie in the symmetry-breaking field, an invisible architect that rewrote the rules of reality in the universe's first moments. Think of this field as a cosmic switch. At unimaginably high energies like those just after the Big Bang, it sat in a balanced, symmetrical state, like a pencil perfectly balanced on its tip. But as the universe expanded and cooled, that balance became unstable. The field fell into a new, lower energy state, like the pencil tipping over. And just as the pencil could fall in any direction, breaking its symmetry, the field's transition wasn't uniform. Some regions of space might have tipped one way, others another, creating patches where physics worked slightly differently. This wasn't just a minor tweak, it was a revolution. The symmetry-breaking field's collapse could have cleaved the single unified force into the four we know today: gravity, electromagnetism, and the strong and weak nuclear forces. The Higgs field is the most famous example of this process. When it shifted from symmetry to asymmetry, particles that were once massless suddenly stuck to it, gaining weight like snowflakes clinging to a wool blanket. But the Higgs might not be alone. Other symmetry-breaking fields could have shaped the cosmos in ways we're only beginning to guess. Take the strong nuclear force. Why does it bind quarks so tightly inside protons and neutrons, yet fade to nothing beyond them? A hidden field might have frozen its strength at a certain scale, locking it into the exact range needed for atoms and life to exist, the wildest implication. These fields might still be active. If the early universes faced transitions left behind defects, cosmic strings, domain walls, or magnetic monopoles, they could linger like scars in spacetime, proof of symmetry's violent breakdown. Even stranger, some theories suggest the vacuum we call empty space is just one of many possible low-energy states. Another symmetry-breaking event could be lurking in our future, a ticking bomb that might rewrite physics in an instant. We're already hunting for clues. Particle colliders like the Large Hadron Collider recreate extreme energies, hoping to glimpse how fields behave near symmetry's edge. Cosmologists scour the cosmic microwave background for imprints of ancient phase transitions, while astrophysicists search for relic magnetic monopoles that could only form if certain symmetries shattered. But the deepest mystery isn't just how symmetry broke, it's why it broke the way it did. Out of all possible outcomes, why did the universe land on this particular set of laws, this delicate balance that allows stars, planets, and life? The symmetry-breaking field might hold the answer. Its choices weren't random, they were written into its structure, a blueprint hidden in the math. And if we can decode that blueprint, we might finally understand why reality looks the way it does and whether it could have been any different. Imagine a substance that doesn't just resist gravity, it actively repels it, pushing away everything around it like an invisible force field set to repel. This isn't science fiction, it's the bizarre concept of negative mass, a hypothetical form of matter that would defy every intuition we have about how objects should behave. If such a thing exists, it wouldn't just fall up when dropped, it would accelerate in the opposite direction of any force applied to it, like a car that speeds backward when you press the gas pedal. And if this strange substance isn't just a fluke but tied to a hidden negative mass field permeating the cosmos, it could rewrite our understanding of everything from dark energy to the very fabric of spacetime. The math behind negative mass isn't just wild speculation. It emerges naturally from Einstein's equations of general relativity. Normally, mass warps spacetime inward, creating the gravity we know. But negative mass would warp it outward, generating a kind of anti-gravity. Picture a trampoline, place a bowling ball on it, and it creates a dip that's positive mass. Now imagine someone lifting the fabric up from below that's negative mass, creating a hill instead of a valley. The implications get weirder when you consider how this would interact with ordinary matter. A negative mass object placed near a positive one wouldn't just hover, it would chase it, locked in an endless acceleration where both objects speed away faster and faster without any added energy. It's as if the universe's brakes failed in reverse. This runaway effect might sound like a physicist's nightmare, but it could solve one of cosmology's biggest puzzles: dark energy. The mysterious force accelerating the universe's expansion behaves eerily like a negative pressure, something a negative mass field could theoretically produce. If space itself is threaded with this exotic field, its repulsive gravity might be stretching the cosmos apart, not as an external, dark energy, but as an intrinsic feature of reality's fabric. Even stranger, this field could stabilize wormholes, those hypothetical shortcuts through spacetime. Normally, wormholes collapse instantly under their own gravity, but negative mass's repulsive force might prop them open, creating traversable bridges between distant points in the universe. Critics, of course, point out the glaring problem: no one's ever observed negative mass. It violates the energy conditions that keep physics tidy, and its existence would raise thorny questions about causality and conservation laws. Yet nature has a habit of surprising us. Quantum mechanics allows for effective negative mass in certain systems, like ultra-cold atoms in carefully tuned laser traps, where particles behave as if they have negative mass. If this phenomenon scales up to cosmic levels, even indirectly, it might hint at a field we've yet to detect. The search is already nudging forward. Experiments with exotic fluids and metamaterials simulate negative mass dynamics, while telescopes scour the cosmos for anomalies in galactic motion that might betray its presence. Whether this field is real or just a mathematical ghost, it forces us to confront a profound truth. The universe might not just contain weirdness, it might be built on it. And if negative mass is out there, lurking in the equations, our cosmic rulebook is far from complete. Quantum mechanics has always danced on the edge of paradox, particles acting like waves, objects existing in multiple states until observed, randomness baked into reality's core. But what if it doesn't have to be this way? What if the quantum world's chaos isn't fundamental, but a veil hiding a deeper order? That's the bold claim of Bohmian mechanics, a radical alternative to mainstream quantum theory where particles are guided by a hidden cosmic choreographer, the pilot wave field. Picture a surfer riding a wave. The surfer isn't at the mercy of randomness, they're carried by the water's precise, invisible motion. In Bohm's vision, every electron, photon, and quark is like that surfer, steered by a hidden tide of energy that dictates its path with perfect determinism. No dice rolls, no probabilities, just a universe where particles have real positions and velocities, even if we can't measure them directly. This pilot wave doesn't just nudge particles, it entangles them, orchestrating their movements so precisely that their correlations appear spooky to outsiders. The beauty of this idea: it reproduces all the predictions of standard quantum mechanics, the interference patterns, the uncertainty, even entanglement, without ever invoking collapse or randomness. Schrödinger's cat isn't both dead and alive. It's in one definite state, with the pilot wave field humming along, aware of all possibilities but committing to just one. It's a universe that looks probabilistic because we're blind to the underlying symphony, not because the symphony is improvised. Critics, though, pounce on the price of this elegance. The pilot wave field isn't just subtle, it's non-local. updating instantaneously across the entire universe to keep particles in sync. That means breaking Einstein's sacred speed of light barrier, not with signals we can exploit, but with a hidden connectedness that defies classical intuition. Worse, the field leaves no trace beyond its effects, like a puppeteer whose strings are invisible to every instrument we've built. Yet Bohm's ghostly conductor might not stay hidden forever. Recent fluid dynamics experiments have brought pilot waves out of abstraction and into the lab. Vibrate a tray of silicone oil just right, and droplets can walk across the surface, guided by the waves they generate, a macroscopic echo of Bohmian mechanics. These droplets recreate quantum phenomena once thought exclusive to the subatomic realm: interference, quantized orbits, even tunneling-like behavior. It's as if the universe left us a clue, whispering that determinism and weirdness might coexist after all. The implications ripple far beyond philosophy. If the pilot wave field is real, it could revolutionize quantum computing, offering new ways to control particles without decoherence. It might even bridge the chasm between quantum mechanics and gravity, since Bohm's framework treats particles as real, space-time-respecting objects, not probability clouds. And for those uneasy with a universe built on chance, it offers solace. Beneath the quantum veil, there's still a cosmos that plays by rules even if we can't see them yet. Whether Bohm's vision holds up or fades into the annals of beautiful but wrong ideas, it forces us to confront a profound question: is randomness truly fundamental or just a byproduct of our ignorance? The pilot wave field dares us to imagine a universe where every electron knows exactly where it's going, even if we never will. What if the universe is built like a cosmic Russian nesting doll, a never-ending pattern repeating from the smallest quantum flicker to the vast web of galaxies? This is the mesmerizing idea behind the fractal field, a hidden architecture where space-time isn't smooth or random, but intricately layered with self-similar patterns at every scale. Imagine zooming into the fabric of reality like a kaleidoscope lens. The same spirals, branches, and fractures appear whether you're observing the dance of electrons or the sprawling filaments of the cosmic web. It's as if the universe has a secret blueprint, one that scales infinitely up and down, binding the micro and macro cosmos into a single, harmonious design. Fractals aren't just mathematical curiosities. They're everywhere in nature: the branching of trees, the jagged edges of coastlines, even the labyrinthine folds of your brain. But what if these aren't just surface patterns? Some physicists propose that spacetime itself could be fractal at its core, a dynamic scaffold where the same geometric rules govern quantum foam and galactic clusters alike. Picture the veins of a leaf. At first glance, they seem chaotic, but look closer and you'll see a precise, repeating logic, one that optimizes energy flow and resilience. Now imagine that logic etched into the vacuum of space, dictating how gravity clusters matter or how quantum fluctuations ripple through the void. The implications rewrite the rules of physics. Take dark matter. Its elusive nature could stem from fractal gravity, where mass interacts differently depending on the scale. Just as a fractal coastline's length changes with your measurement tool, gravity's strength might vary across cosmic distances, mimicking invisible matter's pull. Or consider quantum entanglement. Particles might not be spookily linked but simply threaded through fractal pathways, like ants following unseen tunnels in a mound. Even the universe's accelerating expansion could trace back to this field, with fractal geometry warping spacetime's growth like roots splitting soil. The wildest twist: a fractal universe might not have a smallest or largest scale. Zoom in far enough and you'd find galaxies within atoms. Zoom out and our cosmos could be a speck in some grander structure's fingerprint. It's a dizzying thought, but not pure fantasy. Simulations of cosmic structure formation often echo fractal patterns, and certain quantum gravity models suggest spacetime could be fundamentally granular, not smooth, but built from infinitesimal, self-repeating units. How would we even test this? The hunt is already on. Telescopes like Euclid map the cosmic web structure, searching for fractal signatures in galaxy distributions. Lab experiments with ultra-cold atoms probe whether quantum turbulence follows fractal mathematics. And if spacetime is fractal at the Planck scale, future gravity wave detectors might catch whispers of its graininess in the echoes of colliding black holes. Yet the deepest allure of the fractal field isn't just in its mechanics, it's in its poetry. A universe built this way wouldn't just contain beauty, it would be beauty, a cosmic artwork where every scale mirrors the whole. From the spin of an electron to the swirl of a supercluster, the same patterns would hum, a silent symphony of geometry. And if we ever decode its score, we might find that the universe isn't just expanding or evolving, it's unfolding one infinite layer at a time. Black holes aren't just cosmic vacuums, they're puzzles wrapped in paradoxes. When matter crosses the event horizon, it vanishes from our universe, leaving behind only mass, charge, and spin. But what happens to all the information it carried, the quantum states, the intricate details that made a star or a planet a planet? According to quantum mechanics, information can't be destroyed. Yet black holes seem to erase it completely, shredding the universe's archival system into irrecoverable noise. Unless, of course, the information isn't lost at all, just rewritten into a hidden code, imprinted on the event horizon like cosmic braille. This is the radical idea behind the black hole information field, a theoretical framework where every particle swallowed by a black hole leaves a ghostly fingerprint on its boundary, preserving the past in a language we're only beginning to decipher. Think of the event horizon as a holographic plate. In ordinary holograms, a three-dimensional image is encoded onto a two-dimensional surface. Similarly, a black hole's surface might store all the information about its interior in a scrambled, ultra-dense format, like a hard drive compressing terabytes of data into microscopic pits. The math behind this comes from string theory, where calculations suggest the event horizon could act as a stretched horizon, vibrating with quantum bits that encode everything that falls in. It's as if the black hole isn't a pit but a prison with walls made of frozen time, where the past is etched into its skin rather than erased. The implications are mind-bending. If information is preserved on the horizon, then black holes might not be eternal graves. Over eons, as they evaporate via Hawking radiation, that scrambled data could slowly leak back into the universe, not as recognizable stardust but as a subtle pattern in the radiation itself. Imagine burning a book and then reconstructing every word from the smoke swirls. That's the scale of the challenge, but the principle holds. The universe might have a built-in recovery system, a cosmic control plus Z for black hole deletions. Yet the devil's in the details. How does information transfer to the horizon? One proposal is quantum hair, tiny distortions in the black hole's gravitational field that encode data like grooves on a vinyl record. Others suggest the information field operates through entanglement, with particles inside the black hole remaining mysteriously linked to their counterparts on the surface, like shadows cast by a flame. The wildest idea, the event horizon could be a firewall, a seething layer of quantum chaos where matter is shredded and reconstituted as information in real time. It's not a smooth boundary but a computational membrane processing reality like a cosmic CPU. Critics argue this smacks of desperation, an ad hoc fix to save quantum mechanics from its own contradictions. After all, if information escapes via Hawking radiation, why hasn't anyone detected even a whisper of it? And if the horizon encodes data, what happens when black holes collide? Do their information fields merge like merging hard drives, or does one overwrite the other? These aren't just technical quibbles, they're existential questions about how reality stores its memories. The stakes couldn't be higher. If the black hole information field is real, it would mean spacetime has a built-in backup system, a redundancy that prevents cosmic amnesia. It could also hint at a deeper truth, that the universe is fundamentally informational, with black holes acting as transformers between matter and pure data. That's not just a new physics, it's a new metaphysics where the distinction between stuff and description of stuff blurs into irrelevance. Experiments are catching up to theory. Gravitational wave detectors might someday spot echoes in black hole merger signals, ripples that betray the presence of an information-rich horizon. Quantum computers could simulate microscopic black holes, probing how data behaves at the edge of oblivion. And if we're very lucky, Hawking radiation itself might one day be measured, its subtle patterns decoded like a cosmic Rosetta Stone. Until then, the black hole information field remains a tantalizing maybe, a flickering signal in the noise of paradoxes. But whether it's confirmed or refuted, one thing's certain: black holes aren't just destroying information, they're teaching us what information truly means. What if the universe next door is closer than we think, separated not by light years of empty space, but by a whisper-thin barrier that occasionally tears, letting realities bleed into one another? This is the spine-tingling premise of the multiverse field, a hypothetical framework that could bind parallel worlds together like pages in a cosmic book, each vibrating with its own laws of physics, but occasionally folding just enough to let ink or particles bleed through. Picture a vast honeycomb, each cell a self-contained universe with its own unique constants, one where gravity is stronger, another where time flows backward, or where life evolved from silicon instead of carbon. Ordinarily, these realms would stay forever isolated, their boundaries locked. But if a multiverse field exists, it might act as the cosmic connective tissue, its fluctuations creating temporary wormholes or quantum tunnels between worlds. Think of it like radio interference. Normally, you tune into one station cleanly, but during atmospheric shifts, signals from distant channels flicker through. Similarly, this field's ripples could allow particles, energy, or even information to slip between realities, leaving behind ghostly traces in our experiments. One tantalizing clue lies in quantum tunneling, where particles seemingly cheat physics by vanishing through barriers they shouldn't overcome. Normally, this is explained by probability waves, but what if some of these impossible jumps aren't just tunneling through space, but tunneling across universes? In certain interpretations of string theory, the multiverse field's energy landscape resembles a mountain range, with each valley representing a stable universe. Particles could roll between these valleys, their sudden reappearances in our world resembling ordinary quantum events, except they've briefly vacationed in another reality. The implications spiral into the extraordinary. Cosmic anomalies like galaxies moving too fast or particles with inexplicable energies might not be measurement errors, but fingerprints of neighboring universes nudging ours through the field. Even dark matter could get a multiverse makeover. If gravity leaks across dimensional membranes, its apparent weakness in our universe might just be dilution from a sister world where it's stronger. But the wildest possibility, the multiverse field might not just connect worlds, it could generate them. In chaotic inflation theory, bubbles of spacetime nucleate endlessly in a larger meta-universe, each birthing a new cosmos with random properties. The field could be the medium in which these bubbles grow, its quantum jitters determining whether a newborn universe has 5 dimensions, no weak nuclear force, or a speed of light 10 times slower than ours. We might live in a cosmic froth, our universe just one bubble in a champagne glass we can't yet see. The hunt for evidence is as creative as the theory itself. Some physicists scour the cosmic microwave background for bruises, odd temperature fluctuations that could mark where a neighboring universe once bumped into ours. Others simulate colliding brain worlds in supercomputers, watching for signatures that might appear in gravitational wave detectors. And then there's the quantum lab work, where delicate experiments aim to catch particles behaving as if tugged by invisible neighbors from another dimension. Yet the multiverse field's greatest gift might be philosophical. If true, it transforms the question, why is our universe so finely tuned for life, into which slice of the multiverse aren't we observing? Suddenly, the improbable becomes inevitable somewhere in the infinite foam. A universe like ours had to arise. It's not that the constants are perfect, it's that we're here to notice them in the one corner where they align. Whether the multiverse field is real or just a beautiful speculation, it forces us to confront a humbling truth. Reality might be vaster, weirder, and more interconnected than our best instruments can yet reveal. And if those barriers are porous, the cosmos isn't just out there. It's right next door, separated by a veil so thin, it might already be fraying. For centuries, physics has been a story of unification, a relentless drive to simplify the cosmic rulebook. First, electricity and magnetism merged into electromagnetism. Then, the weak nuclear force joined the party, forming the electroweak theory. The strong nuclear force followed, fitting neatly into quantum chromodynamics. But gravity, the most familiar force of all, has stubbornly resisted every attempt to join the fold. What if this isn't just a temporary hurdle, but a clue? A hint that all these forces aren't just connected, they're different faces of a single, universal field vibrating beneath reality's surface. This is the grand dream of the unified field, a hidden framework where gravity's cosmic curve and quantum mechanics' frenetic dance emerge from the same fundamental rhythm. Imagine the universe as a symphony. We've been studying individual instruments, the violin of electromagnetism, the drum of the strong force, but the unified field would be the conductor, the unseen hand coordinating every note into harmony. String theory paints one version of this picture, where all particles and forces arise from tiny, vibrating strings whose notes determine whether something acts like gravity or light. Loop quantum gravity offers another, with space-time itself woven from interlocking threads of quantum flux. The implications are staggering. A successful unified field theory wouldn't just tidy up physics, it would redefine our understanding of existence. Time, space, matter, and energy wouldn't be separate ingredients. They'd be interchangeable expressions of a deeper structure. Black holes could reveal their secrets, showing how gravity behaves in quantum extremes. The Big Bang's mysteries might unravel, exposing how all forces acted as one in those first searing moments. Even the arrow of time could emerge as a natural consequence of the field's dynamics, rather than an imposed rule. Yet the obstacles are equally profound. The energy scales needed to test unification are beyond any particle collider we could build, requiring machines larger than solar systems. And the math teeters on the edge of comprehensibility, with theories like M-theory proposing 11 dimensions curled into geometries no human can visualize. Some physicists wonder if unification is even a solvable problem, or if we're like ants trying to deduce the rules of chess by watching a single pawn move. But nature loves simplicity beneath complexity. The electromagnetic unification once seemed impossible, too, until Maxwell's equations revealed the hidden symmetry. The same could be true here. Clues might lurk in unexpected places, subtle anomalies in particle collisions, patterns in gravitational waves, or even cosmological data pointing to relics from the universe's unified infancy. The hunt isn't just academic. Crack the code and we wouldn't just understand the universe, we'd speak its native language, unlocking possibilities from stable wormholes to engines powered by spacetime itself. This isn't just physics, it's philosophy. A unified field would mean the cosmos isn't a patchwork of disjointed rules, but a single, elegant equation whispering beneath the noise. And if we ever hear it, reality won't just make sense, it'll sing. From the Higgs field giving particles mass to the phantom field threatening cosmic doom, from the holographic principle rewriting reality as a projection to the multiverse field whispering of parallel worlds, we've journeyed through 30 mind-bending theories where hidden fields aren't just footnotes in physics, but the architects of existence itself. These invisible forces sculpt everything from the weight of an atom to the fate of galaxies, threading the cosmos with connections deeper than we ever imagined. They could explain dark matter's ghostly grip, dark energy's relentless push, even the eerie synchrony of entangled particles. Some might unlock time travel, others could reveal universes beyond our own. The most thrilling part, we're not just spectators. Every experiment probing quantum quirks or cosmic anomalies is a tug on this hidden tapestry, pulling us closer to truths that could redefine reality. So, which theory leaves you awestruck? The idea that black holes encode information like cosmic hard drives, that consciousness might ripple through a field older than stars? Or the spine-tingling possibility that our universe is just one bubble in an infinite froth of others? Drop your favorites in the comments. We're obsessed with these mysteries too, and your thoughts fuel the conversation. If your brain's buzzing with more questions, how could it not be? Hit subscribe and ring the bell. The universe has endless secrets waiting, and we're just getting started. Until next time, keep looking up and never stop wondering. The next revolution in physics might be hiding in plain sight, buried in the quiet hum of a field